Thank you. Okay, so we are discussing Amdahl's law. So I said that if you have a computer and suppose it is taking C1 time to, or not C1, suppose 14 nanosecond time to execute a program. Suppose program is P1, and after some time you assume that you have another computer where all these parts are not modified, but some component of this computer are modified. For example, suppose this component is now modified here. So in that case, how what will be the speed up of this new computer? Suppose this is C1 and this is C2. Obviously, C2 will perform better because not all the modules are improved, but one of the module is improved, right? So in this case, what will be the performance? So that can be calculated using this formula of Amdahl's law. The speed up is execution time before this modification, that means here, and execution time after the modification, the execution time of this. So in this way, you can calculate. So now if we want to calculate execution time after improvement, then this is the formula of execution time after improvement. That execution time affected by the improvement. What is the execution time that is affected? Here, suppose this execution time is affected by the improvement. So execution time affected by the improvement divided by the amount of improvement, how much improvement it has been done, and plus the execution time unaffected. So let me give you an example. So because here you can use Amdahl's law and you can use this term improvement for different parameters. So let me I was giving an example in last lecture also. The suppose we have uh, a a1 to a10. We have an array of 10 elements, okay, and then we have two metrics here. Both are of 10 cross 10 metrics. So what is our task? We have two tasks. First task is to add all this scalar element, means a1 plus a2 plus a3 plus a10. So you add all this and store a result here. And here you have to add these two metrics and you have to store the result here. Again, this result will be a 10 cross 10, right? So now assume that each all are integer, so integer addition. So assume that each addition takes time taken by each addition is called t is for one addition time. So how many addition will be required? Suppose in left side, how many additions are required? Here 10 additions are required, right? So it is 10t. And in right side, how many add operations are required? 100, right? 100 additions will be required because these are two 2D matrices, and you want to just add these two matrices. You are not multiplying it, you are adding two matrices and storing it in a, third matrix. So total time here will be 100t. T is for time for one addition. Okay, so here in this side you are doing 10 additions, so time is 10t, and in right side you are doing 100 additions, so time is 100t. So total time will be 1110t, right? This is the total time to perform this addition. Now assume that you are doing it in a computer, and somehow you can do parallelization in this part. Somehow you can assume that you cannot parallelize, means perform this part in parallel, but you can divide this matrix into multiple parts. So initially assume that you have only one core when you are getting 110t. Now suppose you have here there are 10 cores, okay, and so total 11 cores are there. So, and what I am saying that you cannot parallel, means you cannot pipeline, or you cannot divide this part, scalar part, means you have to perform it sequentially. Suppose, but this part in the right side part multiplication, assume that these part you can divide it into multiple core. How? I am not saying here, just assume that the right side part, that the matrix addition, you can divide it into multiple core, and such that each core can perform this operation simultaneously to improve the task, right? So that we have discussed in last class also, that if you have a program and if you have multiple core, then it is better to divide the program into smaller parts and give the task to all the core, such that the execution can be done simultaneously. So here we will check that how effective it is. Okay, so in that case, what will happen? How much time it will take? First, we can calculate this, that execution time after improvement. What will be the execution time? It will be which part we are improving. 100 is improving by 10 times. 100 right side, because right side initial time was this time, execution time affected by improvement, initial time was 100, right? Now initial time was, ignore t, or you can write t also. Initial time was 100 t. Now we are saying that no, this matrix, this part will be divided into 10 core. So improvement factor is 10, so we are dividing it by 10. So actually this one execution time, this formula we are applying. Okay, so from here, and plus this part execution time unaffected. So what is the execution time unaffected? This t, right? 10t. So from here we'll get 20t, right? We'll get 20t. So it means that if you have 10 cores where you can divide this multiplication, then time will be reduced to 20t. So now let me calculate the speed up. So speed up will be, I am only writing s here. To speed up will be, initially it was 1110t and now it is 20t. So speed up will be 5.5. This is the speed up, right? So now assume that no, I have 40 cores. So I have 40 cores, not 10 cores. I have 40 cores, and now I want to divide the right side into all the 40 cores. And now let me check the speed up. So in that case, again it will be 100t, but now divided by 40 and plus 10t. So it will be 12.5t. And now the new speed up will be 1110t by 12.5t. Okay, so it will be 8.5, 8.8, I think. Okay, so these are the speed up. So the same example I'll use again when I'll discuss the chapter, but here I'm using this example just to explain how what is Amdahl's law is saying. So if you're some part you are improving, then how it is affecting the overall speed up. If this type of questions is there, then you can use Amdahl's law to perform, to calculate the speed up. So the same example I'll use again. So let me discuss the point here also. So you can observe that when I extended the number of core from 1 to 10, right? Then you can see the speed up is 5.5. But when I've extended from 10 to 40, speed up is only 8.8. So the gap, this gap is not significant, right? This gap is not significant. As expected, it's not as expected. So why? So that is the point. So that's why I said it is very challenging that we have a multi-core processor. I have this laptop, that is fine, it has 8 cores, suppose. But writing a software or writing a program which will support, which will give better speed up in this computer, it's very challenging. It's not like that I will just increase this core. You can see that this laptop suppose has 10 core, so speed up is getting 5.5. I'll say no, I'll increase the core, I'll purchase a laptop where 40 cores are there. You will not get speed up. You'll only get 8.8 speed up. You are not getting speed up. But the interesting thing is, if you increase the matrix size from 10 cross 10 to 100 cross 100 or 500 cross 500, then you will see you are getting more speed up in this 40 core. So it means that sometimes program size is also important. If your program size is fixed, suppose your program size is fixed, then it is always not possible to improve the speed up just by increasing core, if your program size is fixed. And if your program size is also increasing, then increasing core will give benefit. So these core in this course are computer architecture. In this course we cannot discuss all the concept that how to write a software, how to write a program. That this is not the purpose of this course. Here we are only understanding what are the means benefit and what are the facilities available in multi-core, and how to write a program which will best fit for this type of computer, that you will understand in other courses. For example, in operating system you will understand it. You will understand it in algorithm, or if you enroll for the course like parallel algorithms, randomized algorithms, and that course also you will understand that how actually you can utilize it. But operating system is a very important course, specifically for computer science people, because you should know the complete concept of systems. So my advice will be take you should understand what is the basics of operating system. If you some of you are not from computer science, then also you can take some NPTEL course or some other online course, and at least you should know some basic thing: what is process, what is thread, interprocess communication, and some thread, what is called thread, how to write multi-threaded application. These points you should know. Otherwise, sometimes we say that, okay, I know C programming. But the question is, if you know C programming, do you have you ever written any multi-threaded program in C? If the question is no, then you don't know C programming. You should know how to write a multi-threaded program. You should know how to write a multi-process program and all. So then only you can say that, oh, I know a programming language. So the same thing is for object-oriented language like Java also, right? If you claim that I know Java, it's not like that calling some libraries and GUIs, right? You should know how to write a multi-threaded program, how to handle multi-threaded program and all. Because the moment you write a multi-threaded program, they will not behave sequentially. And if you watch my extra lecture that I've uploaded, there was a term called fork. The fork is not for creating thread, it's for creating a separate process. The moment you write a single line fork in your program will not follow sequential process. So the way now you debug your C program line by line, and or at max what is there, for loop ho sakta hai, right? And there will be a loop, or there will be if else or switch case, or a function call. So ultimately it is a sequential code, but that sequential property will not be there. So you must know all these things. So make sure you at the end of BTech you should know all these things. Okay, so with this information I'll go back to the book, and let me start from chapter 6. As I said, chapter 6 is parallel processors from client to cloud. Client, you can say this laptop I can consider as a client. Okay, cloud I explained in last, like servers. So most of server we say that if I am scanning some document and my app is saying it will be stored in a cloud, so you have to understand it is storing in a server designed with small computers. Okay, so initially I'll just scroll down. So what is important from this, because exam is very near, and I cannot say that you have to read the entire chapter and understand all the concept. It's not like this. Try to understand all the terms here, important terms. So here you can follow this. What is multiprocessor? See, important terms you should know. And to understand, don't just memorize this term. To understand this term, if it is required to read this section, read it. And only target is to understand all this term, because I cannot give you more tasks, because this is the last only I'm covering this chapter in this class only. I cannot take any other lecture. So what is called multiprocessor, I think I have already explained, right? So you know what is called multiprocessor. Task level parallelism, process level parallelism, that also I've explained in last class. So if you have 4 core, right, and if you are running here P1, P2, P3, P4, there are 4 independent program running on 4 cores. So these are called task level parallelism. 4 tasks are running on 4 different core, right? These are called task level or process level. Yeah, task and process are same thing here. And I said parallel processing program is challenge is if you want to run only a single program P1, and if you have a laptop like this where multiple cores are there, or you can say this is a processor where there are 4 cores and you want to run a single program, how efficiently you can run it. So that is called parallel processing program. So, and that I said that is the challenging part, main challenging part. Okay, so you can see this task level parallelism, parallel processing program, all the terms are mentioned here. So you should only know the terms. That's written a cluster. So last class I explained what is my, I think there was some lectures also here based on nuka, right? S nuka, D nuka. I've covered those in this lecture. So here and on in those lecture I said there are, if there are 4 cores, then all the cores may have sharing some L1 cache, then they will share some a common LLC, right? All the core have their own private L1 cache, then they will share some last level cache. And after that, this is a complete processor, right? This is a complete processor here. In this laptop, there will be 4 processor in the 4 core in the processor, but there is the RAM is shared by all the cores, right? The RAM that is available in this laptop is shared by all the core. So in that case, it is called shared memory processor, right? I last class I explained. Another one is cluster. Suppose there are 2 computers here, right? This one is a computer, this one is another computer. If somehow I connect these 2 computers and create a cloud, then that is called cluster, because this computer has separate physical memory, this computer has separate physical memory, so that is called cluster. So that is also possible, right? In cloud also we normally say that if we have a very big task, suppose I want to maintain a application like IRCTC, right? So in that case only a single laptop may agar multiple core hai, that is also not enough, right? You can understand the load, how much load they handle every day, right? So in that case you may need multiple small computers connected, right? So maybe one computer will handle some task, another computer will handle another task, like this. So in that case those tasks in that case the computers have different physical memories. So this is called cluster. Just remember all the terms, see the shared memory processor, multi-core processor, all the terms you should understand. And in detailed explanation of this is not possible here. If in future sometime if you take a course like advanced computer architecture, then you'll understand all this, or you will find the more detailed explanation of these points. Okay, then last class I said the point that if you want to write a program which can efficiently use all the code, then it is challenging. So now I'll explain something more about why it is challenging. Suppose you have four authors. You want to write a paper. Now, suppose you want to write a book like this, and you have four people who can work for you, who can write for you. So it is not very easy that you can just give that, okay, you write this part, you write this part, you write section 5.1, you write 5.2, you write 5.3, and you can assume that one chapter will be complete by one day. But that is not easy, right? Because you know there are some flow should be maintained, that if you are writing a paper, you are writing a book, each section is not independent. So what actually will happen, that these authors or this writer must interact with each other. Without interacting they cannot write independently. So that's why if you say that, okay, this is p1 and I can divide this p1 into some small parts, suppose like p11, p12, p13, p14, I have divided p1 into four parts and each part will run in one core. Easy to say, but it may be possible that these parts need to communicate with each other. Otherwise it may not be possible to complete a task. There may be some dependencies and all. So this inter-process communication is also very challenging. So inter-core communication, right? Here it is not process, it is called thread, because this is your program. So if you divide it into multiple parts, you will only create four threads, not four process. So then also the threads are communicating in different cores. And now if you threads are executing in different core, if you want to communicate between them, then the entire process of cache coherence is required here, right? I explained cache coherence, right? That if two blocks are shared, then you have to send invalid and all, right? So there are a lot of things here. So it means that if it's not it is also challenging that how to divide the task such that there should be minimum interaction among the tasks. And if the interaction is more, then it will the performance will be less. So this is a major challenge here. And one more challenge, I think is it's written here, the speed up challenge, bigger problem. So if you read this section, you'll understand the same program that I have written, that first left side I will perform 10 scalar addition, and right side I will do one matrix addition. The same problem they have written here. And if you scroll down here, first they have shown this, see, uh, the see the speed up is 5.5 and 8.8, right? So the speed up is not at when you are increasing a number of core from 10 to 40, the speed up is not increasing as expected. But if we increase the matrix size from I think from matrix size from 10 cross 10 to 10 cross 10 to 20 cross 20, if the matrix size, right side matrix size is increased from 10 cross 10 to 20 cross 20, then you can see the speed up is, I think, speed up is 8.2 and 20.5. So for 10 core it is showing speed up 8.2, and for 40 core it is showing 20.5. So it is quite expected, right? So it means that it is written here also, and that see, these examples show that getting good speed up on a multiprocessor while keeping the problem size fixed is harder than getting a good speed up by increasing the size of the problem. Sometime if you want to just fix the problem size, then maybe if your problem size is fixed, then just increasing number of core may not give you benefit. Or suppose you have a 40 core machine, but your problem is like first 10 scalar addition and then addition up to 10 cross 10 matrix, then there is no point to divide it into 40 parts. If you are not getting much speed up, better divide it into 10 parts or better divide it into 15 parts and let other core be ideal. So if the other code be ideal, then maybe you can put them in low power mode, or maybe you can completely shut down those codes so that you can save some energy. Also, you can save the battery of your laptop also. So this is a separate research area. I'm not going to that direction. There are a lot of research going on how to reduce the energy consumption, right? The same I'm saying, suppose this laptop has 40 core and I want to execute the same problem that I'm saying. So I know I can some calculation, I know that there is no point of dividing the matrix into 40 parts. कोई ज़्यादा benefit नहीं आ रहा है. So I'll use maybe with a 15 or 20 core, and maybe other 20 core, if there is no other task is going on, then operating system will put them in ideal condition, or maybe they will completely shut it down or for some time. So in that way we can save power, we can save our battery of computer. So this is very important. There are two power consumption thing there. One is called static power and is called dynamic power. So static power is required even if you are not doing anything in your computer. If you just my computer is on now, if I just put it like this also, but if I see in the evening, then also power will be discharged, right? So that is called static power. Power required to just keep the chip alive, that is called static power. And every time if you access the chip, some additional power you will consume, that is called dynamic power. So saving static and dynamic power both are very efficient, and a lot of research going on in this direction also. Okay, so here this there are two terms you can see here: strong scaling and weak scaling. Strong scaling means measuring speed up while keeping the problem size fixed, and weak scaling means the problem size grows proportionally to increase in the number of processors. So just understand, I have explained you the example, and just remember the terms here: strong scaling and weak scaling. And in both scaling, if you go strong scaling and weak scaling, there is the underlying cache also, right? So a lot of things depend on cache memory also. Whatever I'm discussing from last class, I was not discussing directly cache memories, right? I was just saying there are core, you can divide the task, give it to multiple core, and see how it is performing. But all the core requests will go to a cache memory. So if there is a efficient replacement policy, you can improve the performance then of the cache, then it will also improve the performance of your task that is running on the core. That's why the memory part is also important. But when you go to industry like Intel, they divide their employees in two parts: core employees, core and non-core. So those who works on cache memories on, they normally call their non-core side. So they are not working directly on core pipelining and all. These concepts are not required. And so most of our students who are working on memory side, our students, or I'm saying our PhD students, they only know the basics of pipelining and data path and all, because we are not working on data path branch prediction. Our students are working on memories, non-core part. So but as a initially you should know both, but if you want to do your further research on memory side, then maybe basic knowledge of processor part will be enough. But if you want to do further research on processor part, right, the processor data path, pipelining improvement, the last class I discussed about scoreboarding, out of order execution, right, then you need to study more on this concept that I'm discussing now. But at least you should know basic for both. You cannot work on memory without unless you don't know the basics of processor. Okay, so so I'll not discuss much after this here. So maybe since it is a recorded video, I'll share the recorded video. So from this point you can skip this section and directly go to next section, 6.3. So from tomorrow, from last class, I was discussing about parallel processing or parallel hardware. So in 1960 only, there are the classification exists from 1960 for different parallel hardwares. So first one is called SISD, single instruction and single data set, single instruction set and single data set. So it is kind of your single core processor. Single instruction set, you can say instruction set means you can assume it's a program, and data set means data. Suppose I'll give you the I'll give you a program, right? Write a program to add two arrays and assume that the arrays are stored in a txt file. So what you'll do, you'll write a C program, you'll load that file, you'll read those of data and add it, right? So that is called data. Data is in your txt file. Data is separate. Sometimes we will enter data through scanf, but that is just an option, right? I can say data is in my file or data is in my database. That is also true. Na? So that is called single instructions, SISD. Single instruction means single program working on single data. So that you can run on a single core processor also, right? One program running on one data. Single core processor is enough. MIMD is the multi-core processor that I am discussing from the beginning of this course. The multi-core processor that I am discussing is MIMD, multiple instruction, multiple data. It means that there are multiple programs working on multiple data. Suppose there is a program called P1 performing matrix addition, P2 performing image combining. So data is different, right? First is matrix addition. Maybe it will take data from a file called matrix.txt. Second P2 process is this is a program which is combining two image file. So it will take two image file as data. So you can understand that multiple instruction set means multiple program working on multiple data. So it means that P1 will run here, P2 will run here, P3 will run here, P4 will run here. So I am using this example also from last class, right? So this is an example of MIMD, multiple instruction set, multiple data set. So this is also not very challenging. There are different programs are running on different core of a multi-core processor. But challenging here is in MIMD, you can also run a single program divided into multiple parts. That I'm saying, right? This is which is challenging. So that is called actually single program multiple data, SPMD. So SPMD is not a processor style. The processor style is this. SISD is a processor structure. SIMD I have not explained yet. SI and MIMD is also a processor structure, but SPMD is just a program style that you can run on MIMD. SPMD means single program divided into multiple parts, and you are running it on a multi-core processor, right? So that is called SPMD. So it will run on MIM on this type of multi-core processor only. So basically, every time when I say MIMD, you have to understand that this is the standard multi-core processor that we normally use modern days. This laptop is also MIMD. Okay, this laptop is also MIMD. So this laptop MIMD means I can run if it has 8 core, I can run 8 independent program running on 8 independent data, or I can also write a single program where there are 8 threads, and so 8 thread will work on 8 different core, right? So in this laptop I can also run SPMD. So I hope you are now the SPMD and MIMD is clear, right? So this is how it works. And SISD is the old computer. You can say in 1990s we have computer like Pentium 3, Pentium 2, Pentium 4. Those are single core processor. So in that case, only one program you can run at a time. But still, you may ask a question that in 1998, I don't know in 1998 if I at that time also, if you have a desktop at that time, you can run 2 3 program at a time. You can run a mp3 song, mp3 player. You can run a word file. You can run 2 program at a time and in a single core processor also. But that is a different concept. That concept I'll discuss after some time, or maybe I can discuss it now also. In that case, what happened, at a time only one program is executing, but you know that in computers time is very small, right? In a small time many things you can execute. It's not like a human being. So if you are executing one instruction for a particular program, and that instruction is a cache miss, is creating a cache miss, or it will go to main memory and it will fetch, so it will take a lot of time, right? Or suppose you are writing a program, C program, and it has a scanf operation. Scanf means it will wait for the user to write something, and it is you can imagine how slow it is, right? So in that case that program is useless. It is not using the process. So what will happen if there is these are called input outputs actually. Input output means if I am sending some input or I'm taking some input from user, so those are not directly handled by processor. Those are, if I type something from keyboard, those will handle by some input output manager or input output controller. So if there is a scanf function is there in your program, so those will be handled by input output manager. So it will take some time. So in that time, some other task can execute on the processor. So that is called multitasking. So there is a single core, but that single core can be used round robin fashion for different processes. So that type of parallelism is still possible on a single core also. So but ideally at a single time only one program is executing. But you can see in multi-core, at a single time there are two separate core, and in two separate core two different program can execute, right? That is not the case in single core. Okay, so MISD is a there is no real computer exist for this model. MISD says single program, that is no, sorry, multiple instruction set. There are multiple programs, but there is a single data. So if I can give an example, suppose we have two array like this, or you can say vector. So suppose we have two vectors like this, and there are three programs here: P1, P2, P3. First program is performing addition of these two, second program is performing multiplication of these two, and third program is performing division of these two. So it means that data is same, right? But these programs are doing separate work on this data. So this is an example of multiple instruction, means multiple program and single data. But this is not very popular, as you can say. The concept is there, but there is no computer so far design on this. That's why I said no example today. No computer, no industry, no one has designed any computer for this. Why? Because this type of requirements may be very less, because we will only design computer based on our requirement, right? So maybe the requirement is less and these type of computers are not required. That's why no one has designed this type of computer. But the concept is there. I hope you are understanding the concept, right? But the reverse of this is called SIMD, and this is popular. And this type of computers are called vector processors, and they require some time for graph processing, or some other task. But this type of computers exist, or at least in maybe in some other in our laptops which are actually working on MIMD, there may be some support for SIMD also. So I'm not going for this complicacy, but SIMD means single instruction multiple data. So it means that, suppose uh, I'll use the same example. This is a vector 1 and this is suppose vector 2. I hope you understand what is vector, right? Or you can say it is array, right? 1D array. So now you want to perform the addition of these two vector. So here, a single instruction multiple data, here it means that there will be one instruction, one program only, but it can work on multiple data. So if you want to perform these two addition on MIMD, or on a sequential computer, or suppose you forgot about all the details, the knowledge that we know from our pre-midsem course. Suppose I give you this type of two vectors, and I give you write an assembly language code or write a RISC-V code to perform the addition of these two and store it in a third vector called V3. Can you write it? You can write it, right? It's a very simple code for you. If I give you that there are two vectors v1 and v2, write a assembly language code and perform the addition and store the result in v3, very simple. But you need for loop, right? You need a loop. Why? Because you will perform addition of these two elements, then next iteration you'll perform these two, next these two, next these two. You'll perform like this, and every time you will check a condition. So you need a branch checking condition, and then you need a loop, and at the end of loop you need some register to maintain the indexing, right? For I equal to, all these things are required. So and but if you go with SIMD kind of computer, what it will do, it will fetch a vector at a time, complete vector at a time. And if you just give one instruction, that add, and that instruction will perform addition of all, that same instruction will apply on all the elements simultaneously. You no need to give separate instruction for each element. So that is called vector. So I'll give you an example here. So I hope I have explained you all these terms: SPMD, SIMD. So as I said, you should know all these terms. So here you can see from this point, SIMD in x86. I'm now explaining this section, but you can, if you want, maybe you can exclude this part. Multimedia extension is not required. If you ignore this part, then also fine. Only important in this section, this section is the example that I'll show. Maybe you can start reading from this part, vector. If you start reading from that part, you will see an example here. So I'll not explain this all the whatever what is written here in detail. I'll directly go to this example: y equal to a cross x plus y. So you assume that y and x are vector. So ultimately you have a scalar a, then you have a vector x, then you have a vector y. Okay, so assume that they are of same size, and then you have to perform the addition, and again you need to store the result back into y. So how to perform that is, and in risk v, the way that we know, that is called as that is called SI, means that is called scalar program. So in the program that we write at called scalar, that's not vector program. So here what we'll do, first suppose this is x, this is y, and this is a. So first I'll load a, right, and store it in a register. So this is the first instruction, they load a. So maybe you can see the instructions are a little different, because all the instructions that we studied are only for integer, right? We never deal anything with floating point number before midsem, right? So here you can see fld here. Can you see the program? Can you see the program? It is visible. So FLD just means floating point load, means it will load a floating point value. So that's why FLD, and F0 are same, like you can say like integer register. F0 is a register to store floating point value. So you can say F0 is a register like X3. So in first line they are loading a, storing it in F0. So in F0 I have a is stored in F0, first line. Then second line they are using a index, right? This is just for end of array, so this is just maintaining index, this is not important. Loop is starting from here. So one by one, what they will do, first they will a is already loaded, because a is scalar variable, so they will load it only once. But inside for loop, first they will load x0, right? First they will load x0, and they will perform, then they will perform a plus x0. So see, first they are loading x0 here, right? And then they are no, it's not a plus, it's multiplication. So they will perform a into x0. Okay, then what they need to load now? Now they need to load y0, right? So now they are loading y0. Then after that they will a into x, this part is already done here. So now they will perform this partial result with plus y here. So a into x0 plus y0 ho gaya. So final result is done. So now here again this value will be stored here, store yi. So means what we have done so far is y0 equal to x into x0 plus y0. ये हो गया है in first iteration, right? Then we'll increment I plus plus here. See, these are for increment I plus plus, and again you'll go here in loop, and then again you'll perform the same operation for 1. So this point is clear, you have written this type of code, right? So you can understand the complications. So when you will run, maybe you can see here, if this is the program, I don't know, it is hanged or what. If this is the program, so number of instructions are very limited here, right? You can see in this program. But when you will run this program, so actual instruction count, that is we call it IC, that is called instruction executed. So when you will run this program, suppose the vector size is 100. So when you run this program, the number of instruction executed will be more, right? At least it should be 500 plus, because in every iteration maybe there are 5 plus instructions are there. And if this instruction will repeat, this loop will repeat for 100 times, then 5 into 100 instruction will execute. So 500 plus instruction will execute here. So the instruction number of instructions that will execute is more here, and the dependencies are also more. If you are maintaining a pipeline also, you have to maintain lot of hazards, lot of data dependency, maybe you will need to go for stall, lot of things are required here. But you can see here there is an alternative program written for single instruction multiple data, SIMD. This is a vector instruction. So assume, though it is not there, means RISC-V has no support for vector processor, vector instruction, but they assume that suppose this facility is there. So how you'll do? First you will load a, no problem. The same way you will load a, then you will load the entire, then you will just give one instruction like this, load dot v, means here you are giving an instruction to load the entire vector at a time and store it in a register called v0. It's a vector register. So you are not giving a loading one element from vector y or vector x at a time. You are just writing you have just written one instruction that load this vector from the memory, load vector x from memory. It will load and it will store it in v0. Then what you are doing, then you have given a command that okay, vector x is already in the register called v0. It is a vector register only. So now perform a cross v0, a cross x. To perform a cross x, what you need to do, a is in f0, right? So a is in f0 and x is in v0, so you can write v0 f0. So that they have written here, floating point multiplication dot d dot d dot vs. Vs means one vector one scalar, right? So first one is vector, second one is scalar. As I am saying, these instructions are not practical for risk b. This is just an assumption, because for vector processor are there, are not for risk b. But this, since this book is for risk b, we are taking assumption and I am explaining it. Okay, so here just write one instruction to and tell the computer that okay, perform addition of this vector with this scalar. So it will automatically perform this addition. Okay, and then after this you load the second vector, that is called y, and store it in v1. So y will be stored in v1, and after this you add the result that you have stored, partial result, you store it, add it with v1, and then final result you can store. So you are just giving one instruction per vector, you are not giving instruction for each element. That's why it is called single instruction on multiple data, and that is also, that's why it is called vector processor. If you design a processor like this, then that processor is called vector processor. But it's not like that. It's don't think that if, even if you are giving an instruction that perform addition of two vectors, suppose let me remove all this thing. Suppose I have two vector v1 and v2. So these are the two vectors, suppose, and I have written a command here, add v1 v1 comma v2 and store it in again in v1. Suppose this is a vector command. Suppose this is a vector command. It's, don't think that the processor that is inside processor has parallel addition unit, because ultimately if I say means suppose the size here is 10. So it looked like that the processor has 10 addition unit, right? First addition unit is performing operation for x0 y0, second is from x1 y1. It may not be like this. Maybe there is one addition unit only. Maybe there is one addition unit, and this addition may be performing sequentially, but as a user I am giving only one instruction. But instruction लेने के बाद वो instruction कंप्यूटर के अंदर कैसे implement हो रहा है, that's a different thing. I am not saying about this. I am saying as a user, as a programmer, मैं एक ही instruction दे रहा हूँ, right? I am giving only one instruction, but computer may implement it in a different way. In computer, maybe there is only one addition, so it may add a0 x0 y0, then वो खत्म होने के बाद maybe x1 y1. It may do this, but as a user, I am giving only one instruction. And it so if I go down, I'll show you a diagram. So it may be possible that you have only one adder, so you'll perform one addition at a time internally, or it may be possible that there are multiple adders. If there are suppose the vector length is 10 but you have 5 adders, then you can perform 5 addition at a time, right? So this is called pipelining. So this type of pipelining is also possible, and this pipelining, this concept is called, I think, strip mining. So you should know this concept, what is called strip mining. So let me go up. I've explained this example. So after if you after this you just read this section, and once you read this section you will understand everything. This computer is not scrolling. Let me scroll it from here. Okay, it is scrolling from here, and then you'll see this pipelining section. When you'll come to pipelining section, here the same things are written. This is called vector lanes. Vector lanes means if I go here, there is only one vector lane. It's like highway, right? There is only one way is there in normal road, but if you go to highway, you can say there are 4-lane highway, right? So you can, there are 4 addition of there, so 4 addition can be performed at a time, and after 4 then maybe next batch will perform. So internal implementation may be different, but as a user you are giving only one instruction, that is single instruction on multiple data. So, and you read this section also. If you read this section, you will understand properly what is the main advantage of vector instruction or vector processor as compared to a scalar processor. The processor that is installed in this laptop is scalar processor, and the RISC-V program that you have written pre-MITSEM, all these programs are for scalar processor, right? But vector processor are unique. It's not not there in every computer. That's why I say at the beginning of today's lecture I said MIMD, you have to understand all the laptops, all the computer of modern days are actually MIMD. And vector processors are there, but they use for some special purpose, not for everything. So here in this chapter, you will only see the advantage of vector versus scalar, but it will not say the disadvantage. Disadvantage means every time you may not get this type of data, right? Every time you may not be like that a single instruction you have to apply on multiple data. Means every day you may not go with addition of vectors. So in that case, vector instruction may vector processor may underperform. So that's why modern computers that we use today, or general purpose computers, are MIMD, because the MIMD can perform all the operations. Maybe it will not perform vector, but वो loop लगा के तो कर ही सकते, right? That way I've seen here. That's why though in this chapter you will only find the advantage of vector over scalar, but there are disadvantages. Means not disadvantage, it has limitation. On that limitation, that's why MIMD are more popular. Okay, so no need to read this section. You can ignore this section, this subsection. I think you can ignore because there is no time. I cannot give you all the tasks to read. So you can, so 6.3 is done. Whatever I've explained, that is enough. And you should know these terms because these terms are important, whatever I've explained. And the section 6.4, I'll quickly explain hardware multi-threading. I think this part I've already explained. I said now that if there is a single core processor, how to improve the performance. In single core also, you can write suppose there is a program and program has 3 threads, suppose T1, T2, T3, 3 threads. Then only one thread can execute in this core, right? Because there is only single processor is there. But as I said, if one thread is executing, but this thread is now ideal, it's not doing anything, and if this thread is facing a cache miss, so it will take some time. So in that case, maybe we can replace this thread with T1 with T2. So T2 will also execute, and then if T2 is also waiting for some data, then maybe you can execute T3 also. So in this is called multi-threading. If you have a single core, but you are replacing or you're threading, or one means you are running multiple threads in a round robin fashion. So why I'm saying here thread, why not process? The same thing you can do for process also. I said now in previous in 1990 computers, you can write 2-3 process. MP3 player is a process, right? What PowerPoint is a separate process. You can do the same thing for process also. But suppose if you have 4 core, right? If you have a 4 process, P1, P2, P3, P4, and each process has thread also. It हो ही सकता है, right? P1, P2, P3, P4 सारे process में अपने अपने threads भी है. So it is better to run one process in one core, and all the threads can use the concept of multi-threading in one core. So अगर एक process को if P1 and this core को combine करें, then वो एक single core का problem आ गया, right? यहाँ पे. So why I'm saying this, because if you want to change a process within a like this, then process changing is very expensive, because each process has its independent address space. So वो change करने में, if you want to switch the process, then it is very expensive as compared to thread. So that's why thread changing is easy. So that's why this concept multi-threading, hardware multi-threading is important. Hardware multi-threading means in a single core, if you have multiple threads, you can run it means not parallelly, in simultaneously, or you can say concurrent. So there are multiple multi-threaded concepts are there, and it's called fine-grained multi-threaded. Fine-grained multi-threaded means there are 3 threads, suppose T1, T2, T3. Take one instruction from here, okay, then suspend it, go to the take one instruction from here, suspend it, execute one instruction from here, then again suspend it, execute one instruction from here, one instruction from here, one instruction from here. That is called fine grained multi-threading. So if you go for fine grained multi-threading, there may be some overhead of replacing one thread with another thread every time, but if you ignore that, that is a very good advantage here. If you remember, there was a concept I explained, branch prediction, right? I should have spent at least 2-3 more lecture on branch prediction. This is again a very big area, but at least you know what is called branch prediction, right? If you have a branch instruction, it will take some time to decide, and in pipeline also you need some stall to handle branch, right? So if in T1, in thread 1, there is a branch instruction here, and it will take some time to decide. So no problem, I'll suspend it and I'll go with next one, right? So in this way also I can save some time. Okay. Oh, sorry, no, branch protection, I think suspend is not a good solution. I think this is true for cache. I think if I am if this instruction, there is an instruction here, and this instruction need to go to main memory, so at that time it will spend some time, right? So in this case, there will be no or you can say underutilization of the processor resources, because at that time I can use another instruction. So this is called fine grain. After every instruction you switch to another thread. Then it is called, then the next is called in this concept, what we'll do, we'll not switch a thread after every instruction. We'll switch thread after a certain number of instruction, when there is a huge gap will be there. If there is a thread running, and this thread, we somehow we know that this thread will face a long stop or long delay here, then only we will switch to another thread. This is so this is another category. And last category is SMT. In SMT, that it is saying that no, what the previous two category is saying, you run only one thread at a time. You have three thread, T1, T2, T3. You can only run T1 here, or you can suspend T1 and then you can run T2, right? That I've explained. And but here you can it is saying that it may be possible that there are enough resources in the processor. Maybe there are some adder here, there are some multiplication unit is here, some division unit are here. Suppose thread 1 is not using multiplication and division, thread 1 is only using addition unit, so it means these two are underutilizing. So in somehow we can, if we can use thread 1 here for using the add unit, addition unit, and you can use thread 2 here to use multiplication and division unit, so it means that two threads you are executing at the same time. It's not like the previous two. So this is called simultaneous multi-threading. So if you know the basics, then it is enough, because I cannot go in more detail. And you can realize that whatever you understood from this course, it is just the beginning of computer architecture. If you go with pipelining, then also it is just the beginning. If we go with memory side replacement or whatever, or cache partitioning, this is just a beginning. So this is just a basic. And the in last 20, or you can say in 30-40 years, there are a lot of advancement is happening in any of this area. So if you want to explore, then there is in every area you can explore. So with this, I'll not advise to read anything more from this section. If you know SMT, then it is enough. And after this, if I go down, there is one more section. I'll say ignore all this, it is not required. After SMT, you don't need to read anything from this section. And then the last section is 6.5, multi-core and other shared memory multiprocessor. I'll not explain this section because I've already explained it. Why? Because if I have shared some lecture on NUCA, non-uniform cache access, the same thing here. They say it is NUMA, NUMA, non-uniform memory access, but I have explained it in non-uniform cache access, multi-core architecture, their private cache, their shared cache, this concept, plus cache coherence. So all these things I've already explained. So you can say 6.5 I have already covered. So that is all about chapter 6. In chapter 6, basically we have not discussed any concept in detail. We just understood some terms. What is SMT, why, what is SIMD and all. And these terms are important. At least you should know these terms. These terms will help you in other subjects. Maybe in OS, if you are going if you are taking a subject like parallel algorithms, randomized algorithm, then these terms will be important for you. At least maybe we will not work on it, but these terms will be important. And if you take advanced computer architecture like course, then you will understand this concept in more detail also. Okay, so I'm stopping here, and that's it from the book. So the next three lectures will be out of book. There again, the recent research problem we'll discuss in next three lectures, and only one lecture will be in course that I will discuss. That is on raw hammer attack on the main memory. How you can run a simple C program, and you can flip the bits of main memory. This is called raw hammer attack. So that I will discuss. That this part will be in course, but other two lectures will not be in course. Okay, so I'm stopping here. Thank you.